Hello, welcome to Module 3, Week 1 of our course on Introduction to Dynamical Models in Biology. Here in this module, we will try to make a simplified model, dynamical model, to understand spread of infectious disease. Remember, there are many types of infectious disease, and some of them are very complex, how they spread. For example, take malaria. For spread of malaria, it is a vector-borne disease. For spread of that, you require the vector mosquito, and through mosquito, it spreads among human being. Whereas common cold is a very simple infection, and it spreads from one person to another person without any vector like your mosquito or fly or something like that. So in this module, we will try to model that type of simple spread of infection, like spread of infection of common cold from one infected person to the other. So if you remember, in the second module, we discussed that we have to always simplify the problem and we have to make simplest model possible, and to do that, we have to make certain assumptions. So here, we don't really have a complete graphical model, but rather I can write like this, that for spread of infection, like common cold, you have a infected person. That person comes in contact with a normal person who is not infected yet, and that normal person become infected, so we get two infected persons. And we want to model this process. So from an infected person to a normal person, the infection is spreading, suppose with a rate constant R. So we want to create a dynamical model, ODE based dynamical model for this system. So let us look into the assumptions that we will make before we jump into writing the ODE and creating the model and analyzing it. The first assumption is that we have made a simplified model. So we are assuming that this disease spreads only when an infected person comes in contact with an uninfected one. The second assumption is very important. We assume that everybody in the population come in contact with everyone. That means we are not quarantining, we are not separating the infected people from uninfected people. So everybody mingles with everyone, and when I meet an infected person infected with common cold, as I come in contact with that person, I get infected. Remember, these criteria is important because to create a ODE based model, you have to assume the system is well mixed or homogeneous. That means within a city, within a campus, within a school, everybody can mingle with each other. So every person can mingle with each other. So it is a well-starred system, well-mixed system, or a homogeneous system. So that requirement we have, that assumptions we have made, because that is one critical requirement to make a ordinary differential equation based model. The second one is also coming from that requirement of, for a particular ODE based model, that the total population should be very large. If you remember, in module 2 video, we discussed that when the number of elements, number of molecules, number of people involved in a process are small in number, then even a single change will cause an abrupt change in the process. So we cannot use ODE based model there. To use ODEs to model our process, we have to assume number of molecules, number of people, number of elements, number of components of the process are very large in number. So in this case, as we are modeling spread of infection from one person to another, so we have to assume the number of people in this system is very large. Another interesting assumption that we make is that we are not considering any death or birth. This assumption, although you all know that in a population there will be certain death without an infection, death is a normal process, and there will be also some birth, the population will increase. But what we have done, we have considered that there is no death and no birth. That means total population is constant. That helps us to reduce the complexity in the equations that we'll make. This type of assumption is usually fair enough if we are considering a time period in which the population of the city or the school or the region you are modeling remain constant over time, does not change abruptly too much. And this type of assumption, to simplify the equations, we make very often in other biological processes also. Suppose you are modeling some processes involving 10 different proteins. You will assume that there is no production of new protein molecule, there is no degradation of the old protein molecule, so the total number of proteins in that system is constant. And usually this type of assumption is fair enough if you are dealing with a small interval of time. Another assumption, the last assumption that I will make here to model this process is that no one get cured. Yes, if I get common cold, even without any drug, maybe in 3-4 days I will get cured. But if I assume that, my equations will be a bit complicated. As we are starting the modeling, we will initially make assumption to make the model simplified, so the equations remain simple. As we progress, we may add complexity to the model. So with these 5 assumptions, let us start making the mathematical model of this. Remember, in case of dynamical models, we will use ordinary differential equation to model our process. And if you remember, a differential equation represents the rate of change or of something or rate of a process. Here the process is spread of infection. So we want to know the rate of spread of infection. So we will represent the rate of spread of infection by a ordinary differential equation. And that equation I have written here. dx dt is equal to r into 1 minus x into x. Let us look into each of these terms. X represent fraction of the population that is infected with the disease right now. For example, maybe 2% of the population is infected with common cold right now in my institute. Then 1 minus x is the fraction of people who are uninfected. And r is the rate constant of spread of infection. So dx dt, the derivative of x with respect to time, is the rate of spread of the infection. That is, it is showing the rate of change in population of infected person. It is the rate of change of x. Obviously, it depends upon how many infected person is there and how many uninfected person are there. That's why it is equal to or proportional to multiplication of 1 minus x, this is uninfected population size, into the infected population size, and we have put a rate constant here, r, as a proportionality constant. So in this ODE, x is the dependent variable. X is dependent variable. Time t is independent, and r is a constant, and we call it parameter of the equation or the model. Let us see. Our equation is dx dt is equal to r, a parameter, into 1 minus x into x. If I expand this, 1 minus x into x is equal to x minus x square. That means the highest power of x in this equation is 2. So it is not a linear ODE, it is a non-linear ODE. Now once you have this ODE, we will try to use these as a model and try to answer some basic questions. So what are the questions that I can ask here? I can ask two type of questions. For example, I can ask like this. Right now, we have 2% population which is infected with common cold. And I know the rate constant for spread of the infection, that may be 0.5 per day. Then how many people will be infected after 1 week? So the question can be written in generalized form that at time equal to 0, suppose the fraction of population infected is x naught, then what will be the size of the infected population at time t? This can be one question, and you can ask this question and try to answer this question using this ODE. You can ask a more generalized question also. You may ask that I want to know the overall dynamics of the spread of infection. That means I want to plot something like this, that I will have time in horizontal axis and the fraction of people infected in the vertical axis, and then I want to know how x is changing with time. Is it changing linearly, non-linearly? How is it changing? So, and t may be from 0 to suppose 30 days, something like this. So, this type of second question can also be asked and answered using this ODE based model. So, let us start with the first. To answer this question, we have to get the original function of x with respect to time. And how do we get that? We have a ODE to start with. And remember, a ODE is nothing but the derivative of a function. So from this derivative, we have to get the original function. And to do that, we will do integration, as you have done it in your calculus class. So what I have to do? I have to integrate this thing so that I can get the function of x with respect to time back, function of x in terms of function of time. So how will you do the integration? To do the integration, you have to separate out t and x. So that's what I have done here. I have separated out t and x. By separating out x and t, I get dx by x into 1 minus x equal to r into dt. This dx by x into 1 minus x has to be integrated from x naught to x. Remember, x naught is the initial value of x. And I have to integrate dt from 0 to t. And remember, r is a constant. That's why I have taken it out of the integration sign. This type of integration is very simple. I can do some algebraic rearrangement. Remember, 1 by x into 1 minus x is nothing but 1 by x plus 1 by 1 minus x. So I have separated this one into two terms, dx by x plus dx by 1 minus x. Both these terms has to be integrated from x naught to x, and the second one also has to be integrated from x naught to x. And on the right hand side, you have r into integration of dt from 0 to t. Move further. Using the simple formula of integration, we get dx by x when integrated, give ln of x. When I integrate dx by 1 minus x, we get minus ln of 1 minus x. So that is shown here. Both of them we have to integrate from x naught to x naught to x, and integrating dt I get time t, so it is rt. If we move further, we can rearrange this term and we get ln x by x naught minus ln 1 minus x by 1 minus x naught is equal to rt. These terms can be rearranged further, and we can take the ln on the other side, log on the other side. So we get x into 1 minus x naught by x naught into 1 minus x is equal to e to the power rt. Remember, I want to get x as a function of time. So I want to keep x on one side of the equal to sign and rest of the thing on the other side. So I just did a algebraic rearrangement of the whole thing here. From this I get x equal to 1 by 1 plus 1 by x naught minus 1 into e to the power minus RT. Remember, that's what I wanted. I wanted to know x as a function of time. So we have x on the left hand side and time on the right hand side. R that is here in this exponent is a constant, it's a rate constant. X naught is also a constant because you have decided that at the very beginning that x naught is the initial population size which is infected, or the fraction of the population that is infected. So once I have this one, that means once I have a ODE, that is my model, I have integrated that with initial conditions. Remember, this is my initial condition at t equal to 0, x naught is my value of fraction of population infected. So I have integrated this ODE and I have got this one, this function, x as a function of time. Now this function is all I need to answer the questions that I have raised. So let us try the first question. The first question was that if I have, suppose initial population infected, x naught is equal to, suppose 2% is infected. So that means it is equal to 0.02. Suppose R is equal to, this is the rate constant for spread of the disease, is 0.5 per day. Then my question is, after 20 days, what fraction of people will be infected? So, what fraction of people will be infected? That is my question. I can simply answer this question using this function. So, for in this case, it will be x equal to, I will have 1 divided by 1 plus 1 divided by x naught is here is 0.02 minus 1 into e to the power, if I erase these parts, we have e to the power minus, rate is 0.5 into 20. So this is R into T. This will give me around value like 0.9977. That is approximately 99.77%. So what I have done, I have taken the numerical values given here and plugged them in this function that I have got from the integration of the ODE based model. By plugging this value of x naught, R, T, I get the final value of x, and that is 0.9977, which is equivalent to 99.77%. That means my model is saying if at initial time point I have 2% of the population infected, then after 20 days 99.77% of the population will be infected. So first type of question is answered. Now look into the second type of question. Means I want to know the overall dynamics of x with respect to time. I want to know how the size of the infected population is changing. Is it linear or it is non-linear? Whatever it is. So I want to know that. How can I do it? Remember, this derivative, this ODE is my model, and integrating it I have got this function. So essentially I have to plot this function with respect to time. So that's what I have done here. If you can see, I have t in the horizontal axis, x on the vertical axis, and I have just simply taken different values of t for a fixed value of x naught and r, and I have generated this curve. This curve is initially increasing slowly because obviously initially only 2% of the population is infected. Once in large number of population, a considerable number of people get infected, then the rate of spread of the infection increases further. So in the middle we have a sharp rise, and then ultimately it saturates at 1, that is 100%. That means slowly, by 20 days, most of the people in my population is infected. So the population dynamics of spread of this disease is not linear, it's a non-linear one with a sigmoidal type behavior, S-type behavior. So what we have done in this module, to understand the dynamics and spread of an infectious disease, we have created a very simple model. Remember, we are not trying to model a spread of disease like malaria or dengue or something which involves vector or something, complicated processes. We are trying to model simple processes like spread of common cold that happens every year. To simplify this problem, we have make some assumptions, and we have to make some assumptions which are required to make this model suitable for ODE based modeling. For example, we have to make sure the system is homogeneous or well mixed. That means all people are coming in contact with each other, and the population size is also very large. That means I cannot use this model to model the spread of infection among 5 people or 6 people. I have a large number of population. And then what we have done, we have represented this rate of change in the size of infected people. Remember, the rate in change in the size of the infected population by a ordinary differential equation. While writing this ordinary differential equation, we have made another assumption that the total population of the system is not changing. That has helped to make our equation a simpler one. We can obviously make an assumption of death and birth, but that will make our equation a bit complicated. Then, once I have that ODE representing the rate of change in the size of the infected population, that is my model, I have asked certain questions. For example, I have asked, if I start with a particular fraction of population infected, what will happen after 20 days? I have asked, tell me what is the generalized dynamics of the system. And I have answered this question by first integrating the differential equation to get the function which represent x, this function of time, which represent x. X is the fraction of population that is infected. So I have got the function by integrating, and then I have that function to answer both my questions. We will use this type of approach to model something bit more complex in future. We will discuss them step by step with the assumptions and how to solve them by integrating the ODE to get the function and then answer these type of questions. Thank you for watching. We will build new models in future.